Welcome everybody to our presentation. My name is Anas Yunus. Kees, Jong and I looked into planning and scaling name data networks and persistent identifier interoperability for sharing digital objects using name data networks. From now on, we will call a name data network NDN and the persistent identifier will be called PID. We will start by highlighting our use case CData Cloud. CData Cloud is a distributed infrastructure to manage large and diverse sets of data about seas and oceans. This pan-European network offers data access to support scientific workflows which varies from climate change prediction to offshore engineering. They have 8 institutes with over 100 data centers, and their aim is to make research data available to scientists. They serve very large data sets, which could potentially lead to network congestion. Sharing data also becomes a challenge to scale things up with a lot of load. So in their model, data is pushed to the CData Cloud cache by providers or so-called data hosting organization. The data object then gets assigned a PID when it is stored in the catalog. PID is basically a unique identifier for an object. We will talk about this in the upcoming slides. With a lot of users, this model is not efficient as current cache only duplicates the entire data repository, which is still kind of a centralized solution. So CData Cloud proposed the following model to introduce NDN at CData Cloud. With the NDN, data is cached at intermediate routers or hops. The data hosting organization pushes the object in NDN, where the PID resolver does the translation from PID name to NDN name and inserts the data in the NDN network. The data consumer then can request the object from the NDN network. However, their current model only supports one PID type. Interoperability of different PID types has not been realized yet in this model. We will talk more about NDN in the upcoming slides. Based on the technical challenges at CData Cloud to implement PIDs and NDN, we came up with the following research questions. How to make the PID and NDN namespace interoperable? With the following sub-questions, how to support different PID types and how to incorporate extensibility for future PID schemes. The next research question is how to plan and scale an NDN network. With the following sub-questions, which NDN scaling problems are known, which method can be used to plan an NDN network, and how to deploy an NDN network in a scalable way. We will discuss the following in our presentation. We will give a short introduction about NDN and PID. We will briefly go through some related work. We will explain the system architecture and virtualized NDN functions, where we will discuss PID interoperability and virtual NDN planning, automation, and scaling. Then we will show some experiment results, and at last we will discuss the conclusions and future work. So why choose NDN? Well, NDN is currently the most mature variation of information-centric networking, which is called ICN. In ICN, forwarding is based on name prefixes rather than IP. In NDN, an object name is used to route the data request of the user. There is no need for end-to-end connections, and data is cached on intermediary hubs, which leads to data being cached nearby the client. If YouTube were to use NDN, it would look like this. The videos will be cached at the routers nearby the client. So what's a PID and what kind of types are there? Well, a PID is to uniquely identify an object, like we discussed earlier. Here we show the most widely used PID types, which are URN, handle, DOI, and ARC. All the PID types have more or less the same naming scheme. They all start with some kind of PID identifier, followed by some kind of delimiter. Then you get the authority, which is responsible of the PID resolution, followed again by some kind of delimiter, and the last part is the name. The authority can be seen as a prefix of the object, and the name can be seen as the suffix of the object. For example, I guess everybody here is familiar with the ISBN numbers, which get assigned to a book. The ISBN is unique for each book, independent of its location. If you buy a book and take it home with you, the location changes, but its identity is still preserved. Now we'll go through some related work. Rahav Musa focused on translating DOI PIDs to an NDN name. Rahav concluded that PID to NDN name translation is possible. Her model only supports the DOI PID type. Furthermore, she also looked into the most optimal caching strategy in NDN. Andreas also researched this topic and came up with the following statement. PID to NDN mapping will be highly dependent on the client's NDN browser, which will need to be updated every time a new rule would be appeared or changed. Based on this statement, Andreas proposed to use a PID to NDN mapping server for every PID type instead of doing the translation in the browser. Spiros et al. Created an NDN gateway called NDN as a service for PID, also called NAS for PID, and supports one PID type. Now we will discuss the PID to NDN namespace interoperability that we implemented in our model, which we will show in the upcoming slides. So translation is transparent to the user, which means that the user should not even be aware of an NDN network. The user enters a PID and gets an object back. This is all resolved by the gateway, which is part of the NDN network. The NDN gateway determines whether the user receives the object from the NDN network or from the PID server. Furthermore, it supports there's support for multiple PID types, and the model should be easily extensible with future PID types with different naming schemes. So in this slide, we will explain our model. So as you can see, a client enters a PID, and then step 1, a socket will be opened to the PID to NDN gateway. The PID request of the client is sent to this gateway. This gateway translates the PID to an NDN name in step 3. In step 4, it checks if the object is available in the NDN network. In step 5a, if the object is available in the NDN network, it sends the NDN name back to the client. And then we will continue step 6a. So the name is sent to the client, and then step 7a, the NDN request, the request will be sent to the NDN network, and the object will be retrieved from the NDN cache. In step 9, the NDN object is sent to a router nearby the client, and step 10, the NDN object is sent back to the client from the router that is nearby the client. So if the object is not available in the NDN network, in step 5b, it will send the request to the PID server, like shown in step 6b. And the client will retrieve the object from the PID server if it's not in the NDN network. And in the meanwhile, in step 7b, the PID object is inserted in the NDN network. So the next time a client requests the object, it gets served from the NDN network, which is less time consuming retrieving the object. Kees will now continue the presentation.
So my name is Kees Jong, and I will tell you more about the proof of concept we set up. So first of all, how do you plan this NDN network? Well, as will become more apparent in the next few slides, this is a quite diverse infrastructure that we will set up. It will be composed of different cloud providers. We'll be using different VMs and then also deploy containers on those VMs. So it will be good to have a single description to plan and deploy such an infrastructure so you can keep things manageable. So is there an open standard available? The answer is yes, and it will be explained also in the next few slides. So how to make NDN scalable but also software definable? Well, as I already briefly said, our NDN network is composed out of containers. So with Kubernetes you can deploy and scale these components dynamically. And with SDN style control you can use environment variables which are then picked up by scripts inside these containers to add some certain roles or configure certain routes. So this is an architectural drawing of our proof of concept, and I will go through it in a live demo in the next few slides. So on the left side you have the cloud provider Meloose, and on the right you have the cloud provider Neems. And these two cloud providers can be distributed on a continent. And they're interconnected through an NDN overlay, which sits on top of the Internet TCP IP underlay. So if the NDN consumer, which is in the cloud provider Neems, and you can see that in the right oval figure, if that one requests data that's situated into the cloud provider Meloose, and it will go through the NDN network and then will be locally cached in part by the NDN router. So how to plan such an NDN network with Tosca? And Tosca is the topology orchestration specification for cloud applications. That's the open standard we use to orchestrate this complex infrastructure on the many levels that we use it. It's a declarative domain-specific language which can be written in YAML or in XML. And it's composed out of descriptions, which can be then parsed by an orchestrator and then applied by it. And such an orchestrator can be Drip or OpenStack or any other which is able to parse these descriptions. And Tosca is also gaining popularity. So it's used to describe the complete lifecycle, which can be hosts, such as a VM or container, as we will see in our demo, or software components, such as applications, or network components, such as gateways. So, there are different types in Tosca that you can describe for these building blocks. There are 8 in total, but I will just zoom into 3 of them now. So we have Node, which can be composed out of a container or a VM. But before you can deploy a container, you first need a VM to orchestrate, to deploy it. So with that, you can use the relationships type. So you can set a depends on relationship between these 2 components, and then the container will have a VM once it will be deployed. The orchestrator will make sure of that. So then you also have the interface, which is just a set of hooks to create, configure, start, stop or delete things in the lifecycle of the infrastructure. This here is just an abstract Tosca diagram. We left out many details here. That's because we have the full details inside our report, but just for the sake of this presentation we left out some here to make it easier to understand. So on the left upper side you have the inputs field, and on the right upper side you have the inputs field. On the right upper side you have some constraints as well, like mymem is an integer which needs to be greater than 12 gigabytes, and also some disk size logic there, like it needs to be greater than 100 gigabytes. These are needed for a good working NDN network, and the orchestrator will not deploy, it will give an error once these constraints have not been met. And these VMs, these inputs will be used to set up a VM, which you can see in the center here. So first a VM will be set up, it will be using these inputs, and it will then set up a Kubernetes system on top of which containers will be running. But to set up these containers you also need some input fields. So you can see on the left upper corner some fields there like gateways, routes and protocol. These are environment variables and they will be used by scripts of the containers to set up these fields, set up these parameters. And then you have the interface, which can be used for example to create these routes or reconfigure a route to a different role. So as you can see in the right corner, the scaling in and out the application, there you can see the different container types such as the router, producer and consumer, which run on top of the VM, which you can see in the center. So you can easily scale out the resources and thus also scaling out the application by defining this in the Tosca diagram, which is then interpreted and orchestrated by the orchestrator. So how to make NDN software definable? Well, we did this with Kubernetes, and here's just a snippet of this. The reason we're showing this is because Tosca was not mature enough at the time of writing of our report to fully use Tosca as the center orchestrator. So some of the bits were done with Kubernetes and some of them have been done manually, just to showcase what's possible if Tosca would be fully capable of orchestrating this. So first we set a node name, because otherwise Kubernetes would just deploy it on wherever the resources are available. And when you set a network, it's always very important that the resources are there, because if you set a route to a certain system and that system is not there because Kubernetes deployed it somewhere else, you will have a problem. So in the red you see the environment variables I just discussed as well as Tosca environment variables, but now they're just here in Kubernetes for a proof of concept. Now I'll go quickly through a demo, and I'll first describe what you will see in this demo. So on the left upper side you see cluster control, where we will orchestrate the Kubernetes cluster. Then on the right upper corner you see the cluster status, like NDN consumer 1 is running on node Maloose. And then you also see below that consumer 1 and consumer 2. And those are the containers, and we interactively log on to those containers and then run a few scripts. And those scripts are copy pasted from the copy area you see in the left corner. And what we will do is on consumer 1 we will request a data type, a PID, from the NDN network. It won't be there, we'll get an error. Then we'll request it from the PID. The PID client will then cache it into the NDN, and then we'll do another request from the NDN network, and then it will be cached in there. And the reason we didn't consolidate all these steps into one programming logic is just to highlight the steps that we've took, so you can see every iteration. And then on consumer 2 we will start another query, a separate one, for the same PID object, and then we'll directly get it from the NDN network, because these connections have been set in the NDN network, as you can see in the drawing below. So the consumer in Neems is able to route to the NDN producer in Maloose. So it's time now to show the demo interactively. So first we will start the Kubernetes cluster. Then you can see in the status menu that now the NDN consumer 1 is running on the Maloose node, which is the cloud provider Maloose. Then we interactively log on to the NDN consumer 1 container, and we run our NDN client and then provide it with a PID object. That will fail because it's not already in the NDN network. So then we run our PID client, which will do the lookup for us and then cache it in the NDN network. So the consecutive NDN lookup, which we will do now, once it will request that PID, it will come directly from the NDN network, bypassing the TCP/IP internet connection. So if there's congestion on the internet, you will not have that problem. And also because it's now locally available, you will decrease latency as well. So now we'll extend the Kubernetes network with an extra system on the Neems cloud provider, which is the NDN consumer 2. We then interactively log on to the NDN consumer 2, then run only the NDN client and request the PID from that network. The routes have been set up already, so we directly get it now from the NDN network, bypassing the internet. So in conclusion, we've demonstrated a deployment planning by using Tosca, which is an open standard to create a description of your infrastructure, which then can be parsed by an orchestrator to set up what you've described from a central place to manage. It also showed that we can easily scale in and out to other clouds. So if you're on a certain continent and you want to spread your availability there, then you can do this by describing it in Tosca, and then the orchestrator will deploy these VMs in different data centers. These VMs then can be used to allocate and deallocate the resources. And then Kubernetes, which runs on top of these VMs, can be used to scale in and out the application, which can then bring the data closer to the user, which decreases latency and a chance of congestion. And furthermore, interoperability between PID types is possible by adding different regular expressions. Some future work. So the Tosca blueprints we used for conceptual at the time of writing of our report, so more testing is there needed. The VM that we set up in the Kubernetes was mainly done manually, but if Tosca is more mature by, for example, using Drip or OpenStack, everything can be done from there. NDN is also still experimental, so more benchmarking is needed. We need to test more routing protocols, such as OSPFN, which is OSPF for NDN. And of course, extend Kubernetes with the intelligence that if it sees some congestion somewhere, that it will deploy extra NDN routers somewhere, so that the cache hits are more distributed. And incorporate the PID to NDN translation into the NDN software natively. If you have any questions, then you can reach us at these email addresses. Thank you for your time.